Hello everyone. Today we will be studying some more details about multicollinearity. We already know what multicollinearity is. Multicollinearity is a problem which arises when regressors are highly correlated with each other, which we know leads to near singular nature of X prime X matrix, which thereby inflates the variance. In fact, we have defined VIF, the variance inflation factor, which is used for detecting multicollinearity. Okay, so first let us study what are the various sources of multicollinearity. So there are four primary sources of multicollinearity. Let me list the first one. The first one is the data collection method. Okay. What may happen is the data that we have might be having some issues. For example, if I have suppose two variables x1 and x2, and let me draw the two axes corresponding to x1 x2, so both these are regressors. So it is possible that in my data, when I plot x1 x2, majority of the points lie either in the first quadrant or in the third quadrant. So if my scatter of x1 x2 looks like this, then it would mean that in my data x1 and x2 are highly positively correlated. Of course, we can have a reverse situation. So if we have say majority of the scatter coming from second and fourth quadrant, then it would mean that in our data x1 and x2 are highly negatively correlated, and both of these are problems. So if this is the reason, then we have to make sure that we try to include few more data points which come from other quadrats. Okay, for example, in the positive correlation case, we should try to make sure that we have some points from here and here. Now see, here I am assuming that the centering has been done. Okay, so ideally what this means, see, correlation highly positive, this implies that above average values of the first variable are associated with above average values of the second variable. Okay, so if I want to fix multicollinearity caused by this issue, then I should try to locate such data points where one of the x1 x2s is above average and the other one is below average. Okay, so x2 value is, say for example, below x2 bar and x1 value is below x1 bar. Such cases we should try to locate. Okay, for example, if we are talking of say if we are suppose trying to predict income of a family using say education level of family members. Okay, now it is quite possible that in majority of the families that we collect data on, say husband and wife both are either highly educated or both are having less than average education. So we might end up in this scenario. But it is still possible to locate the families where one of the partners, either husband or wife, has above average education level and the other partner has below average education level. So if we can locate such points, then they will belong to these regions, and adding those points to my data would reduce the multicollinearity. Is it okay? When I say above average, below average, I mean for their own thing. Means if I am talking of husband's education level, then above average education as far as male education is concerned, or below average education as far as male education is concerned. Okay, so of course some of you might be thinking, can I really measure education as a continuous variable? So if I record as number of years of education, then it could be treated as continuous variable. Okay, the second reason for multicollinearity is constraints on the model or in the population. Okay, so sometimes my model itself might have some constraints. or the population. For example, here in the earlier example, it was possible for us to find some families where one of the partners is having above average education and the other is having below average education. But sometimes our variables might be so naturally highly correlated that it may be almost impossible to find instances where such discrepancy occurs. For example, Montgomery has data on electrical consumption. So one of the regressor there is house size and the other regressor is family income. Now we know that if I try to plot house size and family income scatter plot, I am going to get again a positively correlated scatter. And now in this case, it is very unlikely to find a family with very high income but a smaller house size, means something here, or a family with very high house size but less income, so something here. So because my variables are selected in such a way, it is almost impossible to get data on any other region. So in this case, we cannot really escape multicollinearity by simply collecting more data. Here we may have to change the model, means we may have to decide to include only one of these two to reduce multicollinearity. Okay. Third reason is our choice of model. So we have already discussed this while discussing polynomial regression. So choice of model or model specification. So when we were discussing polynomial regression, we saw that if we define our model as say beta naught plus beta 1x plus beta 2x square and so on, then the regressors are going to be correlated. Now because we want a polynomial regression model, this is a constraint given by the model that the regressors are going to be correlated. So in such cases, again, one of the option is we can choose we can choose to drop few of the regressors. For example, if we feel that x square is much more significant than x, then just drop x and retain only x square. Okay. But otherwise, if we want all of the regressors to be in the model, then multicollinearity is going to be present. There is nothing we can do about it. Okay. Another reason is overdefined model. Now, what do I mean by overdefined model? So, this is basically a case where my n is less than p. If n is less than p, then x prime x matrix is going to be singular. Okay. So in this case, of course, there is a clear singularity and our least square estimates will not exist. Okay. So again here we will have to consider some smaller subset of original regressors so that n becomes larger than p and we can go for actual estimation of least square estimates. Okay. So these are the four major sources of variability. Now what happens when we have multicollinearity? So we have seen that why multicollinearity is a problem, because it inflates the variance. We can consider a simple model consisting of two regressors and we will assume that centering has been done. So intercept is not present. Okay, both x1 and x2 have been centered to have zero mean, and hence intercept is not there. So the least square normal equations for these will be x prime x into beta hat is equal to x prime y. So if I actually write this down, then what do I get? What I get here, because I have assumed that the regressors are centered, and additionally we will also assume that the scaling has been done, that is the variances are 1, then what I get is variances here are 1 and I get the correlation between x1 and x2 as off diagonal entry. So I have beta 1 hat, beta 2 hat, and this is correlation of x1 with y, sample correlation of x1 with y, and this is sample correlation of x2 with y. Now when I compute x prime x inverse, what do I get? If we use the determinant and the adjoint, we will get 1 upon 1 minus r12 square minus r12 upon 1 minus r12 square, then same entry here because it's a symmetric matrix, and 1 upon 1 minus r12 square. Now you can see here my variance is scaled up by this factor. So if r12 is very high, then the denominator is almost close to 0, and as a result variance becomes very high. Okay. In fact, the covariance also has r12 square in the denominator, so covariance will also tend to infinity. So large variances and large covariances, which is nothing but inflation of variance, and that is bad for our estimates because our confidence intervals will be too wide. We won't have any confidence in our estimates. Okay, and in fact we have seen that this leads to even opposite signs, means my effect actual beta may be positive, but because the variance of beta hat is high, I might get high value of beta hat with negative value of beta hat with high probability, which leads to opposite conclusions than what is expected. Okay, so in general we know that variance of beta j hat in a multiple linear regression setup with more than 2 regressors, variance of beta j hat will become 1 minus rj square inverse sigma square, where this rj square is multiple correlation coefficient when jth regressor is considered as response and all other regressors are considered as regressors. Correct? So rj square is multiple correlation coefficient between xj and remaining, that is x1, x2, xj minus 1, xj plus 1, xk on other side. Okay, so this along with this group, which we can obtain by simply fitting a regression line with xj as response and these guys as regressors. So r square with this regression line is my rj square. So that's why multicollinearity inflates the variance. In fact, not just that, if we compute deviation of estimated values from the actual values, let me denote it by L1 square. So L1 square is squared distance between estimated values and actual values. So beta hat minus beta prime, beta hat minus beta. Why do we take squared? Because we want a single value. Then expectation of this L1 square will be expectation of this quantity, and which we know is simply a dot product. So this will be sum over I going from 1 to p, expectation of beta I hat minus beta I whole square, and we know all the least square estimates are unbiased. So expectation of beta I hat minus beta I whole square is simply variance of beta I hat, correct, sum over I going from 1 to p, which we know is sigma square times trace of x prime x inverse. Okay, now trace of a matrix is sum of its eigenvalues, so it will be sigma square times sum over 1 upon lambda I, where lambda I, these are eigenvalues of x prime x. Okay, if x prime x is nearly singular, it would mean that at least one of these eigenvalues will be very close to 0. If an eigenvalue is very close to 0, that would mean 1 by lambda I will be very high and this would also be very high, which would mean that the distance of the estimated value from the actual value, expected distance, will be very high. So that is bad. Okay, so our estimates are much away from the actual value in expectation. Okay, so these are the problems caused by multicollinearity. So how do we detect multicollinearity? There are 2-3 methods which come under multicollinearity diagnostics. Okay, what are those methods? One of them, which you might have already seen in our outputs, is VIF, and the other one majorly used is condition indices. Of course, initially we can start by simply looking at the correlation matrix of regressors. So if some of the entries in the correlation matrix of the regressors are very high, when I say very high, I mean very high in magnitude, so the sign doesn't matter, then of course multicollinearity is present. But the converse is not true. What do I mean by that? It means that if all the entries in the correlation matrix are moderate, it does not necessarily mean that multicollinearity is not present. Got it? What is the reason? Because it may be possible that individually all the entries are moderate, but this variable might be a linear combination of say 3-4 variables. So when the combined effect of these 3-4 variables is considered, then only the correlation becomes significant, and that correlation won't be obvious in the correlation matrix. Matrix will tell me only the pairwise relationships. So if there is a clear-cut pairwise relationship, then the correlation matrix will tell me that multicollinearity is present. Otherwise, it may not be enough. So in that case, as I mentioned, we have to go for either variance inflation factors or condition indices. So how do we define VIF? VIF was defined just above, so it is similar, 1 minus Rj square inverse, where this Rj is the multiple correlation coefficient between Xj and remaining regressors. Okay. So if these VIFs are very high, then that would mean multicollinearity is present. Okay. Generally, VIF above 5 or VIF above 10 are considered as quite serious. Okay. The third way to detect multicollinearity is via what are known as condition indices or condition numbers. So what is a condition number? Condition number for X prime X matrix is defined as lambda max upon lambda min. So the ratio of largest eigenvalue of that matrix to the smallest eigenvalue of that matrix. Okay. So it is denoted by kappa. So if kappa is greater than 100, then we say that there is a serious multicollinearity. Okay. So if kappa is between 100 to 1000, then moderate to strong multicollinearity, and if kappa exceeds 1000, then we will say there is a severe multicollinearity. Okay. Condition indices will be lambda max upon individual lambdas. So lambda max upon any jth eigenvalue. Okay. So condition indices, if we have rank of X prime X as P, then I'll have P condition indices. Okay. So again, high values of condition indices will indicate high multicollinearity, and we can also see how many condition indices are larger than say 1000. If only one condition index is larger than 1000, then we need to worry about only one possible linear combination. But if many condition indices are larger, then it would mean that we need a serious reduction in the number of regressors. Okay. So these are some of the ways in which we can detect multicollinearity. Now, what to do? Okay, so we have realized that there is a multicollinearity. how to address this. So how to rectify the problems caused by multicollinearity. Now there are various ways. The first obvious way is subset selection. So drop the regressors which are highly correlated and retain only a subset of regressors. But sometimes that may lead to drop in R square. So that may reduce the quality of fit. Hence people may not be willing to do that. Okay. So the other option is what is known as ridge regression. So what is a ridge regression? Ridge regression is modifying x prime x slightly. See, what we know is x prime x being singular is a problem. So x prime x inverse is a problem. So instead of x prime x inverse, if I compute x prime x plus lambda I inverse, where lambda is some constant, then this may not be that bad. So ridge regression says that instead of using x prime x inverse in estimation, use x prime x plus lambda I, where lambda is a constant. Okay. So what does it mean? My ridge estimates of beta will be x prime x plus lambda I whole inverse x prime y. Now as you can obviously see, if I compute expectation of beta r hat, I will get expectation of x prime x plus lambda I whole inverse, which won't be same as x prime y. So this won't be same as expectation of original beta hat. As a result, the ridge estimate is actually a biased estimate. Okay. Least square estimates are unbiased. Ridge estimate is a biased estimate, but still it is preferred because we said that multicollinearity is causing high variance in least square estimates. So in such case, we are finally interested in minimizing MSE. MSE is variance plus bias square. So right now, least squares are having high variance, hence it's a problem even though bias is 0. So what does ridge regression say? Ridge regression says that okay, I will give you biased estimate. So bias won't be 0, but my variance is less. So the overall contribution from bias and variance will be less. So the MSE for ridge may be less than MSE for least square estimate, ordinary least square estimates. So in such cases, we prefer ridge regression. Okay. In your inference course, you might have seen some examples where unbiased estimate gives you less MSE than where biased estimate gives you less MSE than the unbiased estimate. Okay. Now how to choose lambda? So we know that our problem with multicollinearity is that the variances of betas is high, so they are not stable. So what we generally do is we experiment with various values of lambda, mostly between 0 and 1. In fact, many a times values very close to 0 also suffice. And with various values of lambda, we estimate all the betas. And we plot how betas change when we change lambda. Okay. So this type of graph is known as ridge trace. Okay. So on x-axis we have lambda, various values of lambda, and on y-axis we have various beta hats. So this may be beta 1 hat, this may be beta naught hat, this may be say beta 2 hat, this may be beta 3 hat. Okay. So we have various estimates of beta. And we choose that lambda after which majority of the estimates are stable. Majority of the estimates show flat ridge trace. Okay, they are stable. So this is how ridge regression works. And a third way to rectify multicollinearity is via what is known as principal component regression. So you have already studied principal component analysis in multivariate, and you know PCs are orthogonal, that is they are uncorrelated. So if my regressors are highly correlated, then we will compute P1 as first PC, P2 S score on second PC, P3 S score on third PC, and so on. So the score matrix obtained from principal component analysis of regressors. So I'll have observation 1, observation 2, observation n. But instead of xi's, now I will have P1, P2, Pk's. They will be PC scores corresponding to K PCs. And this I will now use as regressor matrix. Okay. So the PC is obtained, I will use as regressor matrix. Now the problem is interpretation becomes complicated, because if my equation is in terms of P1 and then P1 itself contains linear combination of x1, x2, xp, then interpretation is difficult. But if I collect all the coefficients from P1, P2, Pk of x1, then all the coefficients of x2 from P1, P2, Pk, and so on, then it might be better interpretable. Okay. Another option is, of course, don't take all P1, P2, Pk. Check which PCs are highly correlated with our response y and retain only those PCs which are highly correlated with y. And the third option is choose only important variables from those highly correlated PCs. Means if y is highly correlated with say P2, P5 and P6, then see which regressors have high contribution in P2, P5 and P6 and retain only those regressors. Okay. So these are some of the ways in which multicollinearity can be rectified, multicollinearity issue can be addressed. So we talked about sources of multicollinearity, then how to diagnose multicollinearity, and how to kind of cure or treat multicollinearity. Okay. Let me stop here. Thank you.